Okay, chapter 8 in algebra is, we're getting finally into graphing something other than lines. So this is interesting. We're graphing exponential growth functions, okay? Okay, so we're going to graph and write exponential growth functions. So these look different when we look at the model of them. Because of the words, what do you expect to see? Exponents, good. But we see exponents in a lot of types of functions. And I know you're just used to linear where you don't see exponents. But we do see exponents in a lot of other functions, okay? So what makes these special or unique is that the input, which value in our ordered pair? X, Y. Which value is the input? Everyone? X. That's your input. It's called the independent variable. Put whatever you want in, and then out comes the Y value, right? So that input, X, is the exponent. Okay, so here's your model. Y equals AB to the X. Your input is the exponent. So as we progress through the year, we're going to see other kinds of functions, and you'll never see this again, where the input is the exponent. Okay? So let's look at these other facts about this model. If the model is y equals ab to the x, and we look at a may not equal 0, what would happen to ab to the x if a equals 0? Y would equal 0. That's the multiplication property of 0. And if y equals 0, show me with your arms what that looks like on a graph. Y equals 0. Good job. They're all horizontal, right? They're horizontal. And so we have a linear equation, y equals 0. It's no longer exponential. It's just linear. Okay? Let's look at the second fact here. B's need to be greater than 0. B is this number here. It's the base that's being raised to a power. Okay? So if B was 0, what is 0 to anything? 0 to the, well, 0 to the 0 is a weird thing, isn't it? But 0 to the first. 0, 0 to the second, 0, whatever. So again, we wipe the whole exponential feature out, don't we? Because 0 raised to any number would, I guess, be 0, aside from 0, which would be undefined. So kind of a weird thing. So what happens if B is negative, though? If B is, let's say B is negative 2. Negative 2. What is negative 2 to the first? Negative 2. What is negative 2 to the second? 4. So we have a negative, and then we have a positive. Negative 2 to the third. Negative 8. Negative 2 to the fourth? 16. We go negative, positive, negative, positive. We're back and forth. We don't know where we are. So you'll see when we'll show that later this week. Graphing something like that is just craziness. It's not going to be an exponential function. So you've got to have a base that's a positive. Okay? Positive base. And it may not equal 1, because what if you have a base of 1? What is 1 to the first? 1 to the second? 1 to the third, 1 to the fourth. We're back to having a linear equation, okay? It would just be y equals whatever this number is, a times 1, a linear equation, okay? So that's why we have that rule. So the first thing you're going to be asked to do is write a exponential growth equation given a table or given a graph. If you're given a graph, you have to make a table. Grab clearly defined points in the graph and make a table like this. Because the table is going to allow us to find A and B. So we start with our model. That's what we're writing. And we need to find A and B. Once we have those, X and Y can remain open to any possible ordered pair that works in the function. Okay, so before we get too far into this one, I want you to see some old functions that we've worked with before. So look at, you don't need to write these down, but let's take a look and see if you can identify what kind of a function is this. So do you see a pattern in the domain here? What is it? Plus 1, you know, plus 1 all the way down, right? And what is the pattern in the range? plus 4 plus 4. Can anybody here write the equation of this? Helen?
Y equals 4x plus 4.
Let's see if this works. If we plug in the very first point here, 210, when we plug in 2 here, we get, when we plug in 2 here, we get 8, right? 8? So she wants to change this to 2. 8 plus 2 is 10. It works here. Let's look at the second point. When we plug in 3, we get what here? 4 times 3? 12 plus 2, is that 14?
Yes.
Okay, so this is what type of equation? Linear equation. So what did we see over here? Plus 4 plus 4 plus 4. That ends up being what in the linear equation? Good, it's your slope, right? That's your slope. When you see addition, addition, addition that's constant, that constant rate of change is slope. Okay? And then she found this y-intercept by, we found it by trying this point, right? We tried the point in here and oh, the 4 didn't work, but just add 2 and it works, right? And then we checked it with a second point and it worked. How else could you find the y-intercept? Okay? You could graph it, good. You could graph all of these 3 given points and then it will cross at 2. There's another way you could use this table to find it. Do you remember? Tom? Very good. He says work backwards. So if we go this direction on the table, 5, 4, 3, 2, we could go 1, 0, right? And so we would be subtracting for this direction. And when you subtract 4 from 10, you get
6.
And when you subtract 4 from 6, you get 2. And there it is. It would show up in the table, right? So we could do that. How about this one? Can you do this? Make that equation? Second one. What is the constant rate of change? Plus 10. So what is that in our equation? Slope. So we have 10x. Now we just need to find the y-intercept. So can you back down? Can you go to 1, 0? And when you do, you get? What is your y-intercept? Minus 5. Okay, so we can try any point. If we try this first point, 215, plug in 2, we get 10 times 2, which is? 20 minus 5 is? 15. It works. Try a second point. Plug in 3, you get 30 minus 25. I'm sorry, 30 minus 5 is 25. Okay, so we can use a table to write an equation. In this case, if you see constant addition, and you have a pattern in your domain as well, of just increase by 1, plus 1, plus 1, it's 10 over 1 or a slope of 10. This one is 4 over 1 or a slope of 4. Okay, so today's equations are different. We have exponential functions. Do we still have a pattern in this case in the domain? Do you see it? It's still, so this is good. This is a good place to start. What, and please don't say it out loud. Maybe some of you have already found it, but everybody find it. What is going on in this pattern here, in the y? Hands up when you have it. Okay, Kyle, what is it? Good. He says this is times 4, this is times 4, and this is times 4, so check that out. That would be times 4 as well. So when you see multiplication of the same number again and again and again, now you know I have an exponential function. And so I use this model, okay? And now all I've got to do is find A and B. Okay, so now we're going to talk about how you can find A and B. Okay, so one place we could start is just by substitution, right? What happens when we substitute 0 in as an exponent? What does it do to the base? I mean, anything to the 0 equals what? 1. So if we plug this particular point that I starred here, plug it in. If we plug that into the equation, we have 16 equals A times B to the 0. And I don't know what B is, but when I plug in 0 there, what do we get? 1. So 16, guess what, equals A. So if you have 0, if you have this point, 0, 16, You know your A value right there. It just pops right out for you. This number here is A, okay? And if I know my A value, I can now substitute it into the model. Y equals 16 times B to the X. All we need now is to find the B. Does anyone have a strategy for finding B?
Oh,
What could a person do if you didn't know anything else? Kate,
well, you can take the square root.
take the square root of what?
Or no.
I have 3 unknowns right now in this. 3 things. I have Y, B, and X. Is there any way to narrow this down to 1 unknown? Tom? Plug in a point. Good. We don't want to plug in this point again. That doesn't help us. We already know A is 16. So what would be the next best point? How about this one? This is easy, he says. Okay, good. So plug it in. Plug in 1, you get out 64. So when we plug in this second point here, we have 64 equals 16 times something to the first. So B to the first is just plain old B, isn't it? So 16 times what is 64? So divide both sides by 16 and it's 4. 4 equals B. Now do you see 4 anywhere else on this screen? Where is the 4? How about here? Times 4, times 4, times 4, times 4. The base that you find is the repeated multiplication, okay? We plugged in this point, 164, and B to the first is just B, right? Times 16 is 64, so B is 4. Or we see it is the repeated multiplication, okay? So you don't even have to go do this tough substitution if you can remember that whatever the number is that's being repeatedly multiplied, right? That is your base, okay? So to finish this, the equation is y equals 16 times 4 to the x. There it is. Okay? Now, we're going to write down the steps. The steps are simply this, right?